tremendous and a fantastic ham with us today, and he is Manoj, VU2 Charlie Papa Lima. With CPL is here with us. Manoj, nice catching up with you. Manoj, by the way, is a commercial pilot. He's a high-flying guy, almost at 35,000 feet, always, most of the time, I should say. But nevertheless, thanks to this program, we have grounded him now, at least for the next couple of hours here. And I also see Jack and Al there waiting for you there. So Manoj will be moderating this session. Manoj, as I said, has also worked quite a bit on SDR and has also been very active, although his job takes him off the ground most often than not. So welcome to you, Manoj. Over to you there.
Okay, good evening. Thank you very much for the very kind introduction there, Shankar. And good evening to everybody there. Madhu, thank you very much. I hope I'm audible.
Absolutely, 5.9+.
Okay, thank you very much. Good evening, everybody. Good evening and welcome once again to this wonderful roundtable now. And just a very brief introduction from my side. I'm Manoj, as Shankar said, VU2 CPL. I'm based in Bangalore. And currently I'm working. Actually, I'm out of station, and today happened to be a day when I had some free time, and I'm quite glad to join the discussion and to listen to the very, very renowned personalities, Jack and Al themselves. Thank you very much for this opportunity, wonderful opportunity, to all the organizing committee of HamFest India 2021. Good evening, good morning to you, Jack, and good morning to you, Al. Warm welcome to HamFest India 2021. It's a great pleasure and an honor from our side to welcome you to this discussion. Short word about Jack and Al. They are pretty famous. I'm sure, like anyone who is interested in SDR and homebrewing definitely would have seen at least one of their projects. And Jack, Whiskey Tango Echo Echo, is a very senior person, 1943 born, 1954 onwards. He is a licensed amateur radio operator. And he is currently the vice president of the Milford Amateur Radio Club. And he is also a part of the Greater Cincinnati Builders Group. Quarterly columnist for CQ magazine, and the profession wise, he is a retired professor. He's retired from the Purdue University College of Technology, and he has co-authored quite a lot of books and articles. I'm sure anyone who has seen QST and CQ magazine, I'm sure the name is extremely familiar. And this is particularly on programming, and he is interest is specifically about microprocessors which are used in amateur radio. So that's a wonderful combination of two skills. And Jack, it's a great pleasure to have you on board here with us, and a warm welcome to you. And Al, again, one more very famous personality, I should say, Alpha Charlie 8 Golf Yankee. Even though a latecomer from what I've read about yourself on amateur radio, the licensed amateur radio scene, I've seen that he's been a very keen electronics enthusiast right from his early days, from his childhood, and he's licensed in 2010. And he is as Jack has put it somewhere, the E&D person behind all the projects, and Jack contributes with the software part of all the projects. So without wasting much time, I would like to invite Jack, and Jack can bring in Al as well, and then take us on to this wonderful discussion on the software-defined radio. Over to you, Jack.
Okay, are we okay now?
Can you hear us?
Yes, absolutely.
Yes, you
Please
can.
go ahead.
Okay. This is Al. Al's the EE brains behind almost everything that we do. And so what we're going to do is go through a little slide presentation, and then at the end we'll have an actual video of our project. So what we're going to talk about today.
Well, first of all, we need to turn on the. Can you see the slideshow?
Not yet.
Okay, I think you need to.
Karthik, I'll just a sec. Karthik, can you enable them to share their screen, please?
Screen.
Yeah. Let me come down here. Share screen. Okay. Okay. You've disabled the share screen sharing. You have to turn that on for me.
Yeah, we'll do that. Karthik, my colleague is at it.
Okay.
Karthik?
Sir, I'm doing 1 minute, sir.
Just make him the host, Karthik. I think
Yeah,
that
sir,
should
I have
do.
done. Albert, can you please check?
Can you check, sir, Albert?
Okay, I'll check the. Let's see, one. It should be on. Okay, one. So share screen. And screen one. Select the screen. Ah, oh, I see. Yeah, I've got to turn it on. Never mind. There. Can you see it now? Not yet.
Not yet.
Not yet. Oh, yes.
Yes.
Oh, yes. Coming up.
Very good. All right. Let me make it full screen now. There we go. All right. Now I'll turn on the slideshow. Jack?
Okay. Al and I have been working on this software-defined radio project for almost 2 years. 2 years now. And first thing that we wanted to do, if you'll notice, we've done SDT, not SDR. And there's a reason for doing that. We're calling it a software-defined transceiver, and it's not just an artificial distinction. It's a very real one to us. Most SDRs that most people are familiar with are receive-only devices. And obviously, we're interested in one that can do more than that. And they range in price from very cheap, $10. I've seen some actually for less, to up to things like SDR Play, which are several $100s. And they are very, very good devices. The problem is that they are receive only, and that's not what we're really interested in. So software-defined radio then is just the receive-only devices. We're interested in both receiving and transmitting. So most commercial rigs now have gone to an SDR background, and there's a number of reasons why they're doing that. The real driver behind all of this is cost, of course. You can replace a lot of hardware components with software, which is very inexpensive to implement, and it's very inexpensive to change. And it's the change aspects of it that really drives all of this. The other thing that you can do is you can improve the feature set over time. There are a number of SDR radios out there now, micro SDR, the SDR project done by Keith, a bunch of other ones. And some of those are still using the Arduino 328 family. One programmer named Guido is really just a software genius, and he's managed to shoehorn all kinds of features in the limited resource depth of the 328. We're not that smart, so we've gone to a more powerful processor. Our design goals were a 5-band high-frequency software-defined transceiver that does 80, 40, 20, 15, and 10. You'll notice we're missing some of the bands that are permissible, at least in the United States, for other frequencies. But this is a big enough elephant to chew, so that's what we're sticking with right now. It does both single sideband and CW. It can receive AM, and quite honestly, the software is based on the convolution SDR, which also supported other modes like RTTY, but Al and I aren't set up to do RTTY, so we kind of stripped that out. We're calling this a fuzzy QRP. And the reason we're calling it that is because you can select the power level you wish to use from 1 to 20 watts of power out. And quite honestly, there are just times when 5 watts doesn't get it. So to have the other 15 watts in the bag if you need it, sometimes makes all the difference in the world. I've worked the past 2 field days in the United States running 15 watts on single sideband, and have managed to work almost all of the continental United States. And I've also made some contacts with Portugal, France, and Spain. The other thing that we had as a design goal, and this was one that we think was kind of irritating if you're trying to go to a park or a soda activation or something like that, we don't want to drag along a PC or a laptop or a tablet to have the visual display of the radio aspect of the transceiver. So we want the whole thing self-contained in one box. No external laptop, PC, or other computing power. We want the rig to be trunk portable. And what we mean by that is this is not something that you're going to put in your backpack and walk up an 8,000-foot mountain. You could do it, but you better be an Olympic athlete because this thing's going to...
Mainly because of the batteries.
The batteries to power a 20-watt rig are going to be fairly substantial. If you're running less power, okay, a little bit lighter. But we think that even with the heat sink and a reasonable battery, it's going to be around 10 pounds. For soda activations, doesn't sound like much, but that's actually a pretty heavy load to carry. The last goal that we had was we wanted to try and bring it in at reasonable cost. And what is reasonable cost? Well, it depends on the feature set. And I think when you finish listening to this presentation, you'll realize that we have features that even some of the high price spreads don't have. So to us, the goal was to keep everything under $200. And we wanted it to be easily assembled. And more importantly, we wanted it to be one like Farhan has done with the MicroBitX and the BitX series, where people can hack it. So all of this will be open source, both hardware and software. And we have designed it as a series of 7 boards that if you're not happy with our power amplifier, you can pull ours out and put yours in. So that reasonable cost also includes a lot of experimenting ability that goes along with it. And then, like I said, everything will be open source. We're in the discussion right now with a company that is talking about doing this kit. They think that they can bring the kit in for around $200 to $220. And they will have all of the SMD devices on the boards. So it will be like Farhan's MicroBitX, which I call a semi-kit. In other words, you're going to run wires from a volume control to the main board and so forth. So we're hoping that gets pulled off, and it will make it easier for people who have difficulty getting parts to get everything in one stop. This is the main display screen. And unfortunately, my mouse, I don't think the mouse works. Can you see the mouse move or not?
Yes, sir. It's
Yes.
visible.
Okay, good. Well, it didn't work last time. Okay, up here is, we call it the T41, and the reason that we're calling it that, actually, we're calling it the T41 EP, and the EP stands for Experimenter's Platform. The T41 refers to the Teensy 4.1 microcontroller, which is a real workhorse. Right now, this says that we're on version 79 of the software, so this is pretty old. Al and I just have been working on version 131, so that kind of tells you where we are. This over here is the main frequency display. It's what we call VFO-A. Over here is VFO-B. So we have two VFOs, and you can switch very easily between those. This is the standard S meter that you're used to seeing. This is a reading from that S meter. This is the typical spectrum display that you're used to seeing, and this is the typical waterfall display. Something that's a little different, the center line is the frequency that you're listening to. So we've got 192 listening to, and down here you can see 192 as well. This red line that you see sort of offset from the center frequency is the fast tune frequency. Fast tune is controlled by its own volume or its own rotary encoder. And with about two turns, you can cover the entire 40-meter band. And you can do that without changing the increment. So this thing is always there. The increment is currently set to 50 down here. And I was probably dinking around with this, and I had it set to 50 because I hadn't changed it since I was last on the CW bands. So this whole box down here in the lower right is called the information box. This up here, the spectrum display, the fast tune will move up and down, allows you to change frequency. When you change frequency, the center line stays the same, but the frequency numbers change. In other words, this is always centered on the frequency, and it's the bottom line that will move. Over here, this is an audio plot of the signal that we're currently listening to. And I can tell just by looking at this that it's a male voice because most of the spectrum is concentrated in the lower frequencies. And you'll notice this audio filter is set at 3.2 kilohertz. So we're listening to sideband. And if you go up here, you'll see that we're listening to with a filter that is it's 3.2 kilohertz in bandwidth, and it's minus because we're on lower sideband. We're sampling at 192 samples per second. This is real time. This will bounce up and down in real time. And there is an encoder dedicated to this filter, and you can move this up or down in real time up to 6K, and you can get it down for CW down to 100 hertz if you wanted to. So that is a real time adjustment into the audio bandpass that you have to work with. This is the standard waterfall display that you've all seen. Down here, we have two things called temp and load. Those are actually debug statements. We are monitoring the temperature of the CPU to try, at this time when we were doing version 79, we were trying to determine whether it would be necessary to have a fan or not for the CPU. And if this would go above, I think it was 55 degrees, lights, bells, and fire department was called. All kinds of interesting things happened. Oops. Okay. The load number, let me get that out of the way. The load number is how much of the CPU computing power we're actually using. And version 79 was about 11,000 lines of C code, and we're using 13% of the processor's power to process the entire system. And all of these are changing, of course, in real time. The information box over here, I have the volume set to 100. Don't ask me why I've got it up that high, but I did when we took the picture. The increment 50 notch was for the notch filter. Noise is for the noise filter. Zoom is an interesting feature because it allows you to zoom in. In other words, you can change the zoom factor and this scale of frequency. Like right now, we're showing from 7144 up to 7244. So we're showing 100 kilohertz slice of the band. We can change that to 1/16 of that.
You can also go to 200 kilohertz, roughly 192 kilohertz for the full band. The problem with that is the resolution goes down, so it's a little hard to see things. So we tend to use the 100 kilohertz slice, but you can do twice that.
We also have compression, mic compression built into it. There's a built-in keyer. I've currently got that set for 15 words per minute. There's also a decoder. I'm actually still working on that. It works, but it's not as good as I would hope it is. So I'm shooting for a better decoder. But when the decoder is running, the decoded Morse scrolls across where you see these debug statements down here for temp and load. So if you're listening to a CW station, it will scroll across the bottom down here. The keyer is limited to, I think it's 5 to 60 words a minute. If you can do more than 60 words per minute, you're way, way above me. The AGC, there's an automatic gain control. Right now, it's white, which tells me that this is active. If it were not active, if you turn the AGC off, this would be gray. And if the AGC kicks in, the AGC letters turn to red. So that's pretty much what you see on the display. This, well, before I leave it, this sort of blank space at the top of the screen is for the on-screen menus that we do have. We're not using a lot of those. I'll have more to say about that in a few moments. Okay. Our objectives for the architecture, we're trying as much as possible to move all of the functionality into the software. And the reason, of course, is it's just simpler to do. Any kind of enhancements or changes.
Take over.
Yeah, go ahead. I'm going to let Al, he's the W8TEE guy.
We use a quadrature sampling method for the front end. As you know, SDR can be implemented in a couple of different ways. You can use a direct sample hardware, which you sample at a very high rate. The problem for a low-cost receiver is the chips that can do real-time sampling of RF in the megahertz range are pretty prohibitively expensive. So we've opted for a lower cost using the TALO quadrature sampling situation. And this allows us to get up to 192 kilohertz bandwidth, which reasonably priced ADCs. It's low cost, low insertion loss, and it's easy to implement. Most of the functions that you see on the screen that Jack was talking about are DSP functions, digital software processing. And we do that
Digital signal
processing. We do that to allow a lot of flexibility in what we do. We do a lot of it in the frequency domain convolution to avoid CPU intensive time domain calculations. This allows us to get very sharp audio filters. They're almost brick wall. They're very, very steep. We use an ADC that allows us 192 kilohertz wide spectrum, which for the ham bands is most of them is perfect. And we've opted to go with the major functions that we have on the screen, such as menu, the bands up and down, selecting the filter type, demodulation, and so on, to be accessed using user-friendly push buttons on the front panel. And as Jack mentioned before, everything is modular, both software and hardware. This is a block diagram of the receive processes. I'm not going to go through this in detail. But I wanted to show this to you so that you see the parts that are in yellow are the portions of the receiver that are in software. And the stuff outside that is still hardware. So you can see we have band filters, the quadrature sampling detector, and on the output, we have the audio stages all in regular hardware. But the rest of it, including the Zoom FFTs, display graphics, complex FFT convolution, and so on, are all done in software. So that allows us to change things and to add things, and allows the user to add things as well. The transmit process is very similar. In this case, everything from here on down to here is all done in software. We use a phasing method to get SSB. There's a similar kind of a plot for the CW, which I won't bore you with at this point. But we have various different filters, the Hilbert transforms, and so on, all in software. The output then is done somewhat in hardware, and we have a power amp that I'll talk about a little later. To give you an idea of what it will do, this, for instance, is a plot of the USB bandwidth from the system using the exciter board out to the power amp. And we have a bandwidth here of about 200 kilohertz. And you see it's pretty, about 6 kilohertz. And you see it's pretty flat. What we've done here is we've actually modulated the signal with an input and swept it to get the band that we have. The LSB looks pretty much the same. Of course, it's down here. I want to also note that the lower side band is suppressed, as is the carrier. And these are 10 dB. So we're getting about a 40 to 50 dB suppression of the carrier, and more than that on the other side band. So the exciter works pretty nicely. We also have a set of transmit low-pass filters. These are high-performance 7-element Butterworth filters that we've modified slightly to get better second harmonic reduction. These are still analog filters, but they're tuned for our particular application. And we'll manage the 20 watts plus with no problem. It's possible to use an alternative to these filters that we have designed, and that is the QRP Labs low-pass filter kits. These are very popular. They plug into our filter module PC board, and for those of you that have the filter kits already that Hans Summers has provided, you can use those. Our mode switching between transmit and receive is done electronically using pin diodes. So in the mode switching, there are no relays. The switching is very fast. Turn on is less than a millisecond. Turn off is much less than a millisecond. And we get very good isolation, certainly better than 60 dB. So we're very happy with this filter board. This is an example of our experimentation with the filters. And this shows the 40 meter response for 3 different cases. We tried an original Butterworth filter. That's this line right here. These were designed with the LC program, which is a free software that's out there that allows you to design various different filters with different element numbers. We're using 7 elements in ours, which is the maximum that the program handles, and it's plenty good enough for what we need. So this shows.
Let me interrupt here.
Sure enough.
I forgot to mention that Al and I are also writing a book together for this particular piece of equipment. And we have 18 chapters in it that literally has a chapter devoted to each of the major blocks. And so from antenna to earphones, we have a chapter devoted to a discussion of the literature, the current literature in that field, why we selected what we did, and then a discussion of the actual implementation of it in the hardware
And software.
And all of that will go entirely through the book that way. We also have a chapter that Al thought up was called or is called Just Build It. In other words, we think that the book, when we're done, can almost be used as a textbook. But we also know that there will be people who buy the book that could care less about that. And so they want to just get to the building of it. So we have a chapter called Build It where you can skip to it and just build, have directions for building the T41. And then it ends with a chapter on enhancements. I already have a lot of things that I would like to add to this radio. And I should point out that right now, despite everything that we've implemented, we're using less than 3% of the memory resources of the Teensy. So if you're into software, hardware, fiddling around, you got a lot of resources in that pool at your disposal. Go ahead.
Well, just carrying on. So we tried the regular Butterworth filters. We compared it to a regular Chebyshev filter. And then we came across a paper that was done a while back that indicated how you might improve the Butterworth filters by adding a single capacitor to the center inductor and really cut the response at the second harmonic down to almost nothing. So you see, this is a measured response, and we're getting, with the modified filter, about 75 dB reduction of the second harmonic. We opted to go with this modified version of the filter, and that will be in there for all of the different bands. We talked about the electronic mode switching. This is a simple diagram of what's in it. It's a little bit more complex than this, but basically there are electronic switches between the input to the receiver and from the exciter into the antenna. Now, the two parts of it that are a little bit critical here are the transmit switch from the power amplifier out to the filters, and the receive switch over here, which turns off everything when you're in the transmit mode. Those are where the pin diodes are. And we're using back-to-back pin diodes in one of the areas to give us the high isolation and fast switching. The power amplifier is better than 20 watts on SSB on most of the bands. Uses inexpensive MOSFETs, the IRF510s, which are less than $1 a piece. We're using 25 volts on the finals. The IFR510s work better at a slightly higher frequency. To do this, we use a boost supply that takes our 12 volt input and moves it up to 25 volts. These boost supplies are readily available on the internet, and they cost about $10 or $12 each for a 200 watt boost supply. So it works nicely there. We've included a couple of other features that you generally don't find on inexpensive power amplifiers, and that is thermal protection. So there's temperature compensation to prevent the MOSFETs from going into thermal runaway. And we have current limiting, so we limit the current to the finals to about 4 amps. This is a measured max power per band for our power amplifier. I said it was better than 20 watts. Well, for a short term on the heatsink that we have, you can get 35 watts. I wouldn't like to run this continuously with the heatsink because it gets pretty darn toasty. But on 80 and 40, you can get 35 watts, and the spurious emissions are less than 43 dB, which is the USF FCC rule on spurious emissions. On that same criterion, 20 meters gets 25 watts, 15 about 20, and unfortunately, because the IFRs kind of run out of steam at the high frequencies, you're only down to 11 watts on 10 meters. But we do have 10 meter output, and it's pretty decent. To give you an example of what the spectrum looks like, this is 25 watts at 7 megahertz. Well, here's the fundamental, and this is the second harmonic, which is down more than 50 dB, and the third harmonic over here is about minus 44 dB. So it's even at 25 watts better than the requirements. The second harmonic is typically lower because we use a push-pull configuration for the output, which tends to suppress the even-ordered harmonics. Jack, let you go on to the packaging.
Okay. The packaging is going to be, like I said, 7 printed circuit boards. By design, we made all of those less than 100 by 100 because almost all of the printed circuit board houses have specials where you can buy 5 boards for $1 or something like that. It's just ridiculously cheap. So the packaging of the actual circuitry is on small boards, and those are interconnected with SMA connectors for the most part.
I don't know if you're looking at the small, but this is a typical board. This one is the filter board. It's 100 by 100 millimeters.
And then this is the board that actually holds the toroids that plugs into the one that Al just was holding up. So Hans's filter boards actually can plug into this if you wanted to, but most people, if they have Hans's filters, they would leave this board out and plug directly into the one that Al was holding up. Okay, so the packaging lends itself to portable, but like I said, it's going to be reasonably heavy, especially with a battery pack. So that's why we came up with the term trunk portable. It has to be large enough for a 20-watt heatsink, and we found one that works very well. That is, I don't know if we have one handy here, but
I can show you the.
Yeah, Al's got the.
This is the power amplifier, and here's the heatsink on the back. It's a commercial one I found on eBay. This is the boost module right there. So it takes any input up to 30 volts and gives you out your 25 volts on the other end at up to about 4 or 5 amps.
I didn't have a heat sink, so I used my car's bumper. I mentioned the size of the boards. There's lots of room on each board. There's all kinds of test points on the boards where we can let you hook on a voltmeter and check the voltages and so forth. And then there's enough space that if you wanted to add discrete components, even those with leaded through-hole type components, you could do that. Oh, I should also mention that the SMDs, we're using surface-mounted devices instead of through-hole, but they're all 1206, which is the largest size of SMDs. And like I said, the company that we're in conversation with is going to mount all of the SMDs anyway, so that may be a moot point. You can easily replace any one of those 7 boards if you have a better design. We think that this might be the way that we will do our first real breadboard. You can see up here in the corner, I'm going to be using a 5-inch display. Al's going to be using a 7-inch, and we have one beta tester who's going to be using a 9-inch. So this is a tentative layout. This over here is unusual. Farhan elected to use a touchscreen for his microBitX, and there's also a touchscreen on the micro SDR. And we're not using that. We are using basically push button switches. And the reason is that even with the heat sink and everything, if you start jabbing at the display touchscreen, these big old mitts right here aren't designed for delicate poking around on a screen. So when I go poking on a display screen, I find that my radio tends to walk off the back of the table. So what I do instead is we decided to go with a push button display, and I can take my right hand, put it on top of the radio, and with my thumb, I can press any one of those 16 buttons. There's an article, by the way, those 16 buttons, a lot of people would just dedicate 16 pins, and the Teensy has 51 pins, so it's not like you're going to run out of everything. But Al's bringing up the display.
So here's the, we can get it oriented correctly. There we go. There's the front panel of the current one.
Here's the
Those
push button.
Push buttons over there.
And I can do that with one hand, which I kind of like. And the other thing is we are not chewing up 16 pins for this switch. And in fact, we only use one IO pin for all 16 of these switches. And the November issue that just came out a couple of days ago of CQ Magazine presents the software of how we did the 16 switches on a single analog pin. And as you probably have already guessed, it's just a voltage divider. But it works incredibly well, and it does free up resources that we can use otherwise. This button is menu plus, and right below it is menu minus. And if I do that, remember I pointed up the two slots at the top of the display, and I said that those are reserved for the primary and secondary menus. Well, that's what these two buttons do. They allow you to scroll up and down through the menu, and this encoder over here can be used for, depending on which menu you select, you might have to use this menu encoder to change the value. For example, if you scroll to CW, one of the fields in there is keyer speed. And if you select that with the select button, which is right here, then you use the menu button to set the code speed from 5 to 60 words per minute. So we've put all of the most often used menu items right on the front panel. There's no scrolling through menus. You just boom, you're there and you're done. And right now there are 3 unused menus down at the bottom. This is the zoom that we talked about, and the step is the increment and
Tuning increment.
a tuning increment. And it's very easy. This is the fast tune. Remember the little red line that I showed you? This is the fast tune. This is the regular tune. And this is for messing around with the filters. This is not etched in stone. You can obviously change this to whatever you want. I get irritated. I have a Flex 6400. It just ticks me off that I have to go to the back of the radio if I want to plug in a different key or change the push to talk or mic connection. So I said, enough of that. I'm putting it all in the front, which I did, and the power switch. If you like it on the back, put it on the back.
Or you duplicate it.
Or duplicate it, whatever you want to do. Obviously, the RF in and out is all on the back of the ground connection. So that's a tentative design. Looking down on the radio, like, is that
Yeah,
loose? You can see how there's boards in there. This is the filter board over here that Al was showing you, and you can see all the toroids in there. So this picture on the screen is sort of the way we laid it out. Again, nothing etched in stone, but it gives you an idea of how we envision all of this going together. Down here, he does have a cooling fan, a little tiny guy about this big, but it keeps that CPU nice and cool without worrying about any kind of thermal issues. This is a picture of what we just held up. Like I said, the select button is right here. If I put my hand on the top of the rig, I can use my thumb and I can access any one of those.
You actually don't need to do that. I've got rubber feet on the bottom of it, and you press it.
Well, it's the switches are soft enough that you don't even have to hold it. There's enough mass in the radio to activate the switches. Push touchscreen, not so sure.
Now, one thing about the touchscreen, we've made provision on here, not in the software, but in the hardware, so that if somebody wants to use this version of this screen as a touchscreen, you can do that. You just have to implement the software to make it happen. So that, you know, it's ready for experimentation. That's where the EP comes in.
Okay. This is another downward looking shot here.
I just explain what we got here. This is the power supply. This gives you 12, 3, and 3.3 and 5 volts. The main board, which has the teensy and the DACs.
Show them the fan there too.
Yeah, and there's a little fan right here. This is the receive board. It has a preamp, a software actuated attenuator, and the QSD. This is the excite board, and are the filters. The power amp is over here. I haven't mounted it vertically as I probably would in the case. And this is the boost supply, which could go right over here in this side. You can see the connections are all by ribbon cable. We have IDC connectors on all the boards to allow you to interconnect things, including the power. And we use SMA connectors for the RF signals. You can, if you wish, just direct solder onto the boards if you don't want to use the SMA cables. The interconnects between the audio are with audio cables, and there are plugins for all of those. So, front panel, you see here, this is the switch to the leads to the switch panel, and there are only 3 leads. There's a plus 3.3 ground, and the output from the voltage divider ladder. Now at this point, what we have is a demo, and we've recorded this, so I'll narrate it as we go along. We've actually done on-air testing of the receive portions of this, and you'll get a chance to see what happens. Right now we're in the receive mode, and you can see the display is active.
Point out with the yellow line.
This yellow line is the bandwidth. Well, I get it over here. This is the bandwidth that you see over here, the 3.32 kilohertz. I'll show you changing the filters in a couple of minutes. I've pressed the menu button at this point. You can see I brought up the AGC, and I can change the characteristics of the AGC.
We're using the menu plus and menu minus at this point.
And we're going on. Now we got a signal. You can hear it in the background there. I'm changing various things in the menu again to show you what's there. Nuts. What happened? Did I run out of time?
Shankar?
Hey, no. Perhaps that was the last slide, I suppose.
Yeah. Okay, let me go back to it because I wasn't finished yet. If you don't mind.
Yeah, sure.
Let's see. I don't know if we can fast forward. Yes. So again, we're going through the menus. And we're doing that by pressing the various buttons. This just has a little bit to go. I'll demonstrate a signal here in a couple of minutes.
Meanwhile, just follow the bumpy line.
I'm tuning at this point, so I'm tuning in a signal. And there you get it. And you can see the audio spectrum changes as the audio does. You can get a view of what's going on with the audio. Now, in a minute here, I hope to show you the fast tune. This line would be moving back and forth.
There it goes.
Yeah, there we go. So I can move it to where I want it. I press the select button. And when I press the select button, it'll move to that frequency, which you just saw. So this gives a very brief view of what the system will do. Let me go back here. I'm going to close this out, and so
You'll have to stop the
Turn off.
sharing. Al.
Sorry.
Stop sharing. That should.
Okay. I'm trying here. Well,
Sharing.
yes, I know. Were we off? No.
No, still it is being shared.
Yeah. Well, I've lost the screen that lets me do that. Well, anyway, I don't see it here. Let me see if I can make this larger. Nope. Are we on still? I think I've just messed it up.
Do you have any other slides to show?
No, that's all the slides.
Okay, then probably we'll just take the questions. Then let it be like this. I think it's pretty much fine. If Jack and Al, thank you very much. That was an excellent presentation, and I have some questions.
Yes, please.
Which are being posted on YouTube as well as on the chat box as well. So anyone if you have any questions, please do send it on the chat box or even on the YouTube on the public chat, live chat. You can put it in, and we'll pass it on to Jack and Al. So the first question is from Space Ghost. He's asking how many slices can we run, and can it run remote?
It's designed to run just a single slice right now. I don't know what it would take to do a second slice.
Well, you'd have to have another front end, another quadrature sampling detector at the front end. And while the CPU has the horsepower to handle it, we've elected not to do that in this particular version. But that's something that could be very easily be done by adding a second QSD board.
As far as the remote issue goes, the software right now doesn't even have cat control in it. My feeling is that when I get to that stage, I can probably implement cat control using the standard TRS protocol. That's probably a weekend project. So cat control would be easy. True remote would be a little more difficult, but I think quite doable.
You have to understand, we're talking about a $200 radio here, not a several $1,000 Flex or other high-end system. So there are limitations.
Absolutely. So the second receiver, when we talk about it, like, the second slice or whatever that is, can we do it in the same spectrum? Like you are taking 190 kilohertz. So within that same spectrum, can you get one more like a VFO A and a B?
Well, you switch back and forth between the VFO A and B, and what that does is changes the local oscillator frequency. Again, we only have one slice available to us. So by adding a second QSD board, I think it would be possible to get that. It's not something we've tried. And in the scope of the book that we're working with, we're probably not going to do that. That could be something in the enhancements or a later project after this is finished.
Okay, great. So that's for Space Ghost. I hope that answered your answered your question there. And Nitin TYZ, U3 Tango Yankee Golf, wants to know whether with the present hardware, by any modifications of software, does this radio can do 2 meter and 70 centimeters?
No.
Well, that's not with the present hardware. That would be a function of a brand new front end on the system, or translating the frequencies down to one of the lower bands. That would be probably the easiest way to do that. We're limited on the hardware to the 30 megahertz, and I think our layout and everything else is designed within that realm. To go higher, will probably take a redesign of the filter boards and certainly the QST front end.
Yeah.
Okay, so with the current hardware, it's not possible with the present setup. Yes,
No.
okay. And Pramod, V2 Tango Papa wants to ask a question. Why not use 12-volt Mitsubishi transistors instead of the IRF 510s?
Well, that's a really good question, and I intend to do that. And principally, it's a matter of cost. The IFR 510s are very inexpensive, and for an experimenter who is working with this thing and with these MOSFETs that tend to be somewhat delicate, you can blow the front end by slipping your probe in the wrong spot when you're making measurements, and you've just shot anywhere from $15 to $20 pair, well, each pair of finals. So I prefer to do all of the experimentation with the cheap ones. When I'm finished with this, I intend to use some of the Mitsubishi transistors. The 16s, for instance, are quite capable of putting out the 20 watts that we need. They're a little bit pricey compared to this, but once we've debugged it, now the power voltage capabilities for the Mitsubishis has to be limited to about the 12 or 14 volts. They won't be able to manage the 25 volts, so that has to be changed as well. So you need a higher current capacity, but it's on my list of things to do.
We also selected the 510s because they're sort of the MOSFET cockroach. They're readily available, they're cheap, and if you blow one, you don't have to go out and mow another lawn to get a new one. So for right now, it works well, and it's within our design parameters, so that's kind of what we stick with. Al's more adventuresome. He's got the ability, I don't. So he'll probably do some experiments with the Mitsubishi.
Okay, great. That's great. Thank you. One question from U3OOI Prasanna. He has a question. What's the sensitivity of the receiver in S levels or dBm or in microvolt levels? Any measurements done?
I have not done that experiment, and I really don't have the equipment to be able to measure the ultimate front end capabilities. I have compared it, however, with my Flex 6400, and anything the Flex can hear, I can hear as well. So, I think the sensitivity is in the same range. Again, we're not talking about a $2,000 transceiver here. We're talking about a couple of $100. But we have no trouble hearing the DX or any low-level signals. Most of the lower bands are limited by atmospheric noise where we are. At the higher bands, you have a possibility for some additional low-level signals, but I'm pretty satisfied with what I'm able to hear. Again, I don't have the microvolt measurement capabilities to be able to make those measurements.
Okay, great. What's the title of the book? You mentioned that you'll be writing a book coming out. So
the book's almost done, and I don't know if we have a title. I think it's going to be building the T41EP software-defined transceiver, something like that. And we're publishing it. It'll be published through Amazon. So we'll put an announcement on our website and make that available as to when the book actually appears on the shelf.
Okay, fine, great. And so where can we find the updates for this? I would put it in a different way. So the website is named Software Controlled Ham Radio. So if you do an internet search on Software Controlled Ham Radio,
our site should come up. Just join and you'll be up to date.
Okay. Okay, fine. You have any plans to make this as a kit?
Well, we are talking with a company, fairly well known, and we think that they're going to market it as a kit, and they're shooting for a target price, which includes all the SMD devices and everything. It may not include the display because there's a option for a 9, 7, or 5-inch display, and those cost around $40. They start around $40. And I'm not so sure that the company wants to warehouse all of those displays. So my guess is it's going to come in around $200 without that display. You can build it yourself for substantially less than that. But the convenience of having all of the components on the board and so forth might be worth the extra couple of bucks.
On the subject of the boards, of course, we have all of these boards designed, and we will make the Gerbers available on the site when we do that. So if you want to get together with a few friends and order numbers of the parts and order numbers of the boards, it's a pretty inexpensive way to proceed. Okay, nice. Great, thank you. And just one question. I think I don't see any other questions there, so probably I'll ask that question from my side. Does it do FT8?
Digital modes are not built in. That's a hardware issue, and it's also got something to do with pushing on the duty cycle too. It's a little higher on the. Well,
no, actually, I have tried the power amplifier at 20 watts with a 50% duty cycle for 15 minutes, and everything worked just fine. I ran out of patience at the end of 15 minutes, turning it on and off every 15 seconds. So it should do FT8 just fine. And the FT8 is another one of those things that could easily be built in as a software edition. If we get time, we'll look at it, but probably we'll go with that as being one of the enhancements that we'll suggest that people work with. But from a hardware capability, the power amplifier can handle the duty cycle. Same with CW. You can run it at 20 watts on the lower bands.
Yeah, I forgot.
No problem at all.
I forgot to mention the Teensy is capable of reading USB port type of data. There's also the Teensy 4.1 has an SD card reader built into it. So one of the enhancements that I'm going to work on when I get done with the basics is I'm going to write a logging program that will put out an ADIF file. And I think on CW, I can actually parse the other person's call using my decoder, or using when you do your part of the exchange and you send their call, I can record that. Date and time clock is already built into the processor. So all of the information I need for logging is really there. Write it out to the SD card, and then when you get home, plug into the USB port, read the ADIF file, and submit it to a controller, wherever. So there's all kinds of enhancements that I would like to put on this, but right now our goal is to get it out the door.
All right. Okay, that's great. I think any more questions, please? I think Surya had asked the keyword search is leading to some other group. So the keyword is actually software controlled ham radio, not software defined ham radio. So probably that will
software
controlled ham radio. Yeah.
So we have a lot of projects that aren't radio related, really.
Yeah. Okay. Fine. Any more questions? Anybody wants to ask anything? We'll pass on to Jack and Al. If there is nothing, probably I think we'll conclude the discussion.
Well, thank you all for your attention.
Yeah, we appreciate it. We're looking forward to getting this out there and having people starting to play with it.
Okay, great. So I don't see any further questions there. So Jack and Al, thank you very much from On behalf of all the viewers, both here on this platform as well as on YouTube, and from the organizing committee of HAMFest 2021, I would like to thank both of you for spending the lot of your precious time and to explain to us the nitty-gritties of your new project. It's excellent and it's very interesting. I'm also not an expert on home brewing, but definitely would like to try out a few things. So definitely when it comes out, we'll give it a try. I had tried the QCX, so I can see some remnants of QCX and QDX there. So probably I can relate to some part of it. So probably will be able to enjoy building it myself, just like many of our friends here, Jack and Al. Thank you very much once again. Have a great day. And
Thanks,
Madhu
everyone.
and Shankar,
Appreciate it.
Yep. Okay.
back to you.
Yeah.
Thank you,
thanks.
Albert. Thank you, Jack. It's been a pleasure talking to both of you. For your information, we have 37 viewers on YouTube and 55 on the Zoom direct link.
Very good. Thanks again, people.
Bye now.
Shankar, go ahead. Shankar,
Okay.
all yours.
Yeah. Okay. Thanks, Jack and Alan, for great presentation and the kind of work that you have been doing on the transceiver. And as Manoj said, we'll certainly put our hands and mind into it and try to dig out whatever best can be done. That's the very spirit of amateur radio, all about, all across the world. And so on behalf of the organizing committee, I would like to thank both Jack and Alan, and of course, thank Manoj, WU2 Charlie Papa Lima, for having taken his time off and moderating the session. And thanks, Manoj, great moderation. And before I end this, I have a couple of things that I would like to say. I would like to thank my colleague Karthik here, who had been with me all around and helping me out, organizing the whole thing. Karthik, you have done a great job, Karthik. Thanks very much. I think probably I'll disturb you tomorrow also there, Karthik. And also I should really thank my company, Excelsoft, for giving access to this Zoom license, the corporate license of Zoom, where we are using it uninterrupted without any interruptions of 30 minutes or anything. So I'd like to thank both of them. Certainly, thanks goes on to all the hands who made it today to this amazing 100 years of amateur radio event. Tomorrow, great lineup once again, a round table of the repeater custodians of India. Saravanan from Mysore, V2 Echo Tango Sierra, has some very interesting thoughts that he would like to share tomorrow. And we will also have a session on micro SDX, MAN and PE1NNZ. The guys who really did the micro SDX would be there with all of you tomorrow too. And on behalf of the organizing committee of Surya, Madhu, Saravanan, Kesri, Ramas, and myself, I would like to thank each one of you. Have a great and a safe day, and we will certainly catch up with you tomorrow evening at 1600 hours.
73, bye all.
73, good evening.
Thank you. Thank you, everyone.